Now in question 6, we have a series of reactions that we need to predict the products for. As we've said before, the key to problems like this is recognizing the reagents and knowing what these reagents do. I would also just sort of warn you, going ahead, given that this is the end of Organic 1, that right now these questions should be pretty straightforward. And that's because at this point, the only reactions that we've learned are for alkenes as well as alkynes. So we specifically know we're looking for that functional group and how the reagents behave with that functional group. As we get into Organic 2, these types of problems get more complicated because many of these reagents can react with many other functional groups as well. But for now, we're primarily dealing with alkenes and alkynes. Part A, we're adding diiodomethane and zinc copper, which tells us that this is a Simmons-Smith reaction. And while you certainly do not need to memorize the names of all the reactions, it's never a bad thing to be familiar with those. What does a Simmons-Smith do? Well, it converts an alkene into a cyclopropane ring. Part B, we have the addition of HCl to an alkene. This is a Markovnikov addition, where the chlorine goes to the more substituted carbon and the hydrogen to the less substituted carbon. In part C, we're adding chlorine, which means we add a chlorine to each carbon. But remember, you should also show stereochemistry where it matters, and when you add a dihalogen such as chlorine to an alkene, that addition is always going to take place trans. Right, part D is the hydroboration reaction, and we know that hydroboration reacts again with alkenes, so we can ignore these two rings at the bottom. Why? Well, these are aromatic rings and they won't react under most conditions that alkenes react. So the reaction will take place up here where the alkene is. Hydroboration is an addition of hydrogen and hydroxide, one to each of the carbons. But it's different from our other hydration reactions, and that's because the hydroboration is an anti-Markovnikov process, and so will give us the alcohol on the less substituted carbon. All right, in part E, we have what looks like an alkylation of an alkyne. So we're adding the strong base, which is able to remove this terminal hydrogen. But the electrophile, the alkyl halide in this case, tert-butyl bromide, this is a tertiary alkyl halide. And tertiary alkyl halides are too big, too bulky to function as electrophiles in reactions like this. And so what will happen in this reaction? Most likely nothing, at least not in terms of the alkyne alkylation. It turns out this will undergo a different reaction, and that's a reaction that we will learn about in the first couple of weeks of Organic 2, known as an elimination reaction. We don't need to worry about that at this point, but it will not undergo an alkylation reaction. And again, that's because the alkyl halide, and specifically the leaving group, the bromine, is too sterically hindered. Right. The addition of lithium and ammonia, the dissolving metal reduction, is the reaction that can convert an alkyne to a transalkene. And so we can draw that in here. What will this do to an actual alkene? Well, nothing. So that part stays the same. In part G, we have the halohydrin reaction, addition of bromine and water. But all we have is an aromatic ring. There's no alkenes present. So this one will not be able to react. Part H is a hydration under acidic conditions. That's a Markovnikov process. And so the OH goes to the more substituted carbon and the hydrogen to the less substituted carbon. And finally, part I is an ozonolysis reaction, and we recall that cleaves the alkene, and in doing so it forms a carbonyl on each side of the alkene and completely breaks the carbon-carbon bond to give us this product.